Okay, now that we've introduced tensor notation for our Lorenz transformations and the electromagnetic field tensor, there's one big thing we need to do. It's really to rewrite electrodynamics, making full use of this tensor notation. So when thinking of Maxwell's equations, of course, we've got the electromagnetic fields, but let's start with the actual sources. So we should try to write our sources in an intelligent way. So what we're going to do is we're going to consider a certain charge density of sources, and this charge density is going to be moving. So what we'll consider is a little volume V of of charges moving around. Okay, and we will say that the charge in this is going to be some total charge big Q, and it will be moving at velocity some u. Okay, now what we would have is that the charge density would be Q over V, and the current density would be rho times the velocity of this whole thing. Okay, so this would be in the lab frame. In the rest frame of the charges, of course, things would be a little bit different because there would be a proper density which would be different to the one measured in the lab due to Lorenz contraction. So the proper density would be Q over V0, where V0 is related. So this would be the rest volume. This would be related to the volume measured in the lab by the relation 1 minus u squared over c squared V0, right? The lab would see a shrunk volume as compared to the rest volume of the charges. Okay, so that immediately gives us the following relations. We have that rho is equal to rho 0 times 1 over 1 minus v squared. Well, sorry, u I'm using over c squared. And we'd have that the current density would be rho 0 times u with the same factor, 1 minus u squared over c squared. Okay, now you see in this expression here, we recognize the proper velocity that we defined. So what we can do is put this current and charge density together into a 4 vector that's called the current density 4 vector. Okay, and this this is just defined as follows. I have J mu is equal to rho 0 eta mu. Okay, and this thing, if you want, is you can write it in components as c times rho jx jy jz. Okay, now the fun bit is that this allows us to write the continuity equation in a very simple way. Okay, so you remember our continuity equation that told us that d rho dt plus the divergence of J was equal to 0. So what does that translate into here? Well, you see, if I just take the notation that I take the J mu with respect to the x mu is equal to 0, I would get the right thing. Because you see the d dx0, x0 is just c times t. So d dx0 is 1 over c d dt. So 1 over c gets rid of this one, d dt rho, this one. And now d dx1 is just d dx. So you see the other terms give me the divergence. So I immediately get that this is my new version of the continuity equation. Okay, very clean. Now, the fun bit is that Maxwell's equations become super simple. Okay, so you remember our field tensor. So what we're going to do now is we're going to take differential of f mu nu with respect to x nu. And in this notation, once again, there's implicit summation over the new index, same as here. Okay? Now the statement is that these are my Maxwell equations. Well, yours too. Okay, so this seems quite miraculous, but nonetheless, that's what happens in physics. Okay, so you have to understand that each of these equations is really 4 equations, because I can choose my index mu to take one of 4 different values, and the same thing in this other equation here. So how does this work? Well, I mean, for example, we can do a super simple one. So mu is equal to 0 in this one here. So what do I get? You remember my F0 blah was just the electric fields over C, right? So maybe I can show it to you again. This one here, right? So 0, 0, 0, 0, 0, 1, 0, 2, 0, 3. Okay, so what do? I want to do the summation of df mu nu, dx mu when mu is equal to 0. So df0 nu dx nu is equal to 1 over c, because that's an overall factor in our thing, d ex dx plus d ey dy plus d ez dz. Okay, so that should ring a bell. This thing here is just 1 over c with the divergence of E. Okay. So on the right-hand side, I get mu 0 times J0, but J0, we've just defined it, it's C times rho. So what I get is that this is mu 0 C times rho, but since mu 0 epsilon 0 is equal to 1 over c squared, that means that really mu 0 J0 is equal to rho over epsilon 0. And ta-da, sorry, there's an extra factor c, right? So I need to put a factor of c mu 0 c rho, 1 over c squared, mu 0 c rho. Hang on, mu 0 c rho. Yeah, so the c goes. So then I've got left over 1 over c epsilon 0 c, like this, right? So combining these two gives me Gauss. Okay? And then you can show similarly that the other laws are obeyed. So, so again, you can see also that dg0 nu dx nu, that just gives that the divergence of B is equal to 0. Okay? And for the other components, I'll let you do them as an exercise. It's very straightforward. but you can see that you can recover also Ampere and Faraday and Ampere Maxwell using these relations here. Okay, it's not complicated. Okay. Now a few more comments. You can write also a number of other things that we had seen. So the Minkowski force. Okay, so on a charge Q, I should say, yeah. So this Minkowski force takes the form now of 4 vector K mu is equal to Q F mu nu in terms of the nu here, proper velocity, okay, and essentially with components K is equal to Q over, again, I'm just using the proper velocity factors here, and then I have E plus V cross B, sorry, U. I'm using U as the velocity here. Okay, so this is just the Lorenz force, and then the Minkowski force. You remember there was this factor of gamma appearing in the relation that that we had. Okay, so that's another kind of simplification for things. So if you want, these are the fundamental equations from which you can do the whole of electrodynamics in relativistic settings. Just these fundamental ones. Okay, so quite simple. Once again, the continuity equation is a consequence of the Maxwell equations with these definitions. Okay, now one last thing to treat. It's the question of how to write everything in terms of potentials. So let's do this little section quickly. Relativistic potentials. Okay, so what we had was that the electric field was minus the gradient of the scalar potential with the time derivative of the vector potential, and that B was just the curl of A. Okay, so what we can do is we can group the potentials in a 4 vector. And this 4 vector will be A mu, and will be by definition V over C, and then AX, AY, AZ. Okay, and now what we can see is that the field tensor takes a simple expression. F mu nu is equal to dA nu dx mu. Okay, careful with the orientation of the indices, and the denominator of the index is down, in the numerator it is up. Okay, so the positioning of this index is correct. Okay, again, the proof of this is just a substitutional exercise. I think you just have to do it and see. If you look at the inhomogeneous Maxwell, because the homogeneous ones, as you remember, are automatically fulfilled, then what did we have? We had that df mu nu dx nu was equal to mu 0 j mu. So what does this become? Well, it means that I just do this replacement here, and say I do the left hand side here, so I would have dA mu, and now I do a double derivative, right? So I would do dx mu dx mu. Okay. And then I just have to be careful with my indices. Minus derivative again of a mu with dx nu dx nu. Yeah, that's it. Okay. So this whole thing would be equal to mu 0 j mu. Okay, now there's a thing that we can do is we can do a little trick using gauge invariance. So the gauge invariance here means that we would change the a mu into an a prime mu, which would be equal to a mu plus total, a simple derivative of a scalar function. Okay, and this thing leaves f invariant. Now we can choose the Lorenz gauge, different Lorenz, no T. This guy was a Danish guy. And in this case, the Lorenz gauge that we had seen when we did the potentials chapter, the notation for this one here is again particularly simple. Just says that a mu dx mu, you remember it was just the total derivative of the thing, this would be equal to 0. So that's really quite nice, because it means that we lose one of the terms in the thing here. You see, we lose the dA nu dx nu term here. This would go, and there would only be this one left. Okay, so if we introduce a notation an object that's called the D'Alembertian operator. This is denoted by a squared squared, and by definition, what is it? It's just d dx mu d dx mu. So again, you just sum over the mu. That's a mu, yeah. And what is this? It's really just the Laplacian minus 1 over c squared, the second derivative with respect to time. Then if we go back to this equation here, choosing the Lorenz gauge so that this term vanishes, we only get this one left. Okay? And we obtain that the whole of Maxwell's equations are expressed in this way. Okay, and that's it. This is the whole of relativistic electrodynamics condensed into, if you want, the most compact, the most aesthetically pleasing formulation that we have. So that's all there is to classical electrodynamics. Okay, this is the most beautiful form for Maxwell's equation. course, you got to know what the symbols mean. It's not just, you know, a simpler equation. They are exactly the same equations than the ones that we already had. Nonetheless, the notation has become extremely economical. You can certainly remember those things by heart, and then the whole application of it changes with the circumstances, but at least the core of the theory has been synthesized to something which is extremely, extremely compact and economical. Okay, so that is actually it for the subject matter of the course. Now you have a couple of weeks to really, you know, well, actually 3 weeks to warm up before the final exam, so I hope you'll be able to go through the material again. I'll send you emails again with suggested exercises. We've got some other preparatory exercises for you. I hope you enjoyed the course. I hope this was just your first you know, foray into more advanced electrodynamics. There are plenty of much more interesting things starting to happen from this point onwards. Of course, you could really spend your life doing applications of electrodynamics, say in matter. We haven't discussed that very much here beyond waveguides. There's a lot of stuff to be done there. We can start talking about radiation, how things work on that front. Again, you can spend your lifetime on that. And then we haven't even begun talking about quantum mechanics coupled to electrodynamics. In more advanced courses, you could learn properly quantum electrodynamics, which essentially starts from many of the things that we've seen here, but adds all the quantum elements to it, making it an extremely rich theory. So quantum electrodynamics is really one of the more satisfying theories within your reach once you've, you know, finished your bachelor's and perhaps decided to go on with a master's in physics. Anyway, it was a pleasure teaching you. Not my laptop, but you. I hope these videos proved to be of a certain use to you, and we'll be in touch. Thank you very much.